All right, let's do a very quick refresh on some of these core concepts. Um, yeah, so actually, hang on one second. I need to get that over there a little bit further. Okay, perfect. All right, so actually, can I? No. Okay. All right, so let's draw something out here. Wish I could draw. All right, so let's say this is our parameter space for a very basic model that has two parameters, theta 1, theta 2. Okay. Now let's imagine there's like a loss surface in here. Like something like that. Something like that. Okay. So if you were to kind of look at it from this direction right here, you would see something like this. Okay. 3D maybe, I don't know, do something like, it is dropping down to this middle area, right? Okay. And there's some bottom to this. Okay, I don't know if that's gonna make sense, but yeah, it's like a ravine. Okay, it's pretty contrived, but it is the way that this stuff is typically thought about. Okay, so let's say that we are currently here. Let's say that we're here. Our current model, you know, has some parameters either trained up to this point or, you know, initialized at the beginning of training such that we live here in this two-dimensional space. And obviously this space is this kind of coming out of the page dimension I'm showing a topology of is the loss of our system, which is a function of the current parameters of the model, our data x, or data y. Yeah, some loss, and we're trying to minimize the loss. Like this, we want to be here, right? Ideally. Now, in previous video, we discussed, you know, the forward pass, the backward pass. So basically, you know, in the forward pass, we compute a prediction, right? So quickly, very quickly, draw a little diagram here. So I got some data, okay? Got our model, okay? Pass data through our model. Our model produces a prediction, right? And we're going to feed that into a loss function, okay? And we have the true labels here, which will also be fed into the loss function, okay? To produce a loss value, okay? Then we compute d derivative of the loss with respect to our model parameters, which we'll call g for the gradient here. And then basically go back, update our parameters, and then do it all over again. It's kind of a keep running through this DAG over and over, although it's not a DAG. the way I've drawn it, but you get the point. So the way we do our parameter update is so theta at time step t is going to be equal to theta at the previous time step minus alpha times the gradient at this time step. Right, and this is the gradient t. Okay, theta is, or alpha here is the learning rate, and so you can also, I will say that's important to recognize that gt is a vector or some tensor or multi-dimensional data point that lives in the space of the parameters. So like in this case, you know, our parameters are living in two-dimensional space, and so we'll say like R2 just for this example. Okay. So this is a vector. This is a vector. These are the same dimensions. All theta t minus 1, and gt are all same size vector, tensor, matrix, whatever. So we can think about this gt on our little visualization here, and like in this case, with it being a valley, and I'm actually going to draw negative gt, but like this right here, kind of visualize our gt as this this vector here. Okay, and basically it points downhill, points down the steepest part of the loss surface at this point. Okay, specifically locally at this point only. GT is the direction of the steepest descent. You can actually say it's negative GT. Okay, and you can imagine. Okay, well first, let's get a little bit more practical about how we compute GT. I think in the previous video, we were kind of looking at just one data point, right? And one data point here, okay? But in reality, you know, you have a data set like this, okay? Like that has maybe n data points, okay? Before we're kind of thinking about just one of these n points. But you know, I guess like this loss surface as drawn, as visualized, is the surface as it like for the joint data set, or joint data set. This is the surface, okay? So if we only compute the gradient for one data point, it's actually gonna be pretty noisy. And so like on our true surface, you know, just doing updates with only one data point is gonna cause like some pretty wild jumping around, a lot of noise, a lot of error, okay? Now if we were to pass the full data set, all n data points through, we could do something like this. We could compute our gradient at time step t be equal to I 1 to n of gt. We'll just notate it like this. Okay, gti is the gradient computed for data point I in here somewhere. Nope. Okay. So basically, just take the average gradient across all the data points, and then that would actually give us like kind of that would give us this actually, the actual true gradient. But again, you'll notice that this is pointing, because it's so steep, it's like a ravine, right? It's like really steep in this direction, really steep. So like this gradient is going to be kind of dominated by like this direction going across, which is not going to be super efficient. We'll get back to that. Now, stochastic gradient descent, passing just one data point in, like you might end up like, over here or, somewhere crazy, like or even backwards sometimes, okay? But at least whenever you pass in the full data set to compute the average gradient over your data set, you know that you're actually taking you have the correct step direction according to the gradient at least. But then, okay, again, this is not what's done in practice. So what's really done in practice is you would, you actually batch this up into blocks or batches of data points of size m, right? And so you would end up with n divided by m batches. But even this isn't enough in practice. Again, because we're, this learning rate, we're scaling down the gradients. Learning is not, it's not like a closed form solution, right? We're applying an estimator, trying to say approximate steps toward the solution in like an iterative fashion. Versus some models, you can actually, there's a closed form solution to the parameters, and so you just need to process your data set once, compute some values, run those values through like some closed form equation, and then boom, you have your fully trained model. That's not the way that neural networks trained with gradient descent work. You actually need to train over your full data set multiple times. So that's called an epoch. So we'll actually, have like multiple epochs, right? Where again, we'll batch every epoch still. But basically it's kind of like the outer loop of the training loop is over your like full data set. And at the beginning, you'll shuffle all these data points, and then you'll just kind of like split them up into fixed size batches, and then you iterate, doing your forward and backward passes and your updates, iterate over batches, and then whenever you finish an epoch, you reshuffle the data, and then rebatch it or whatever, and then just keep iterating over these batches again. So you're visiting data points multiple times. That is how it's done in practice. Yeah. So, and it's like a nice trade-off because obviously, we can't fit all this in memory for practical use cases that would blow up GPUs and computers and be super inefficient. On the other side of that extreme, just passing in one data point at a time is noisy, and it's also really inefficient from a compute perspective. Mini batching, which in practice is just called batching. I don't think I've ever really heard the term mini batching. Mini batch is used in practice, but so when I say batching or a batch, I mean a mini batch. All right. Well, so we've covered, gradient descent, back propagation, chain rule. Talked about like stochastic gradient descent versus full gradient descent versus batch gradient descent. And we've shown the update, the kind of baseline naive update equation for training and updating your model weights, just by moving them in the direction of the gradient at every time step, every iteration. which again is this direction defined by the gradient is pretty heavily influenced by like local topology of the loss surface. We've specifically shown like this like ravine looking, like valley looking shape, and we've shown that the steep valley walls will tend to dominate the direction of the gradient, which you know which would mean potentially, and again just for intuition sake, you might see like a path that looks like this, bouncing back and forth up and down the walls of that valley, gradually moving the direction you want, but really wasting your time getting there. And I guess in reality, one of these steps could have taken you off somewhere else into a less desirable neighborhood. So what we like to do is kind of smooth this out. This is like very this path is very erratic, naive, and highly sensitive to like local irregularities in the terrain here. And also this approach here does not have any sense of the past, like no information from the past, and maybe what sort of trajectory have we already taken up to this point. So basically there are some things that are done to make this a little bit smarter, a little more efficient. So the first thing I want to talk about here is exponential moving averages. Okay, which is going to be a key concept for the next steps here. So, yeah, I'll just kind of define it, write it out real quick, what this is. What is an exponential moving average? So, let me write this out real quick here. I'll explain it. Okay, so this is kind of the general form of a exponentially or an exponential moving average. This is your moving average at time step t, and g at time step t is the new observation, and v t minus 1 is the value of the moving average in the previous step. And then you have beta, which is defined to be something less than 1. And 1 minus beta, this kind of distributing the weight across these two terms. But of course, like these coefficients sum to 1, which is important. And so this actually does have the effect of, if you had, some kind of value here and time step here, and you had like a bunch of data here, like this, right? This, if you applied this moving average to this, it would maybe look something more like right, smoothed out over just like a line plot between the points. And, of course, G, think of that as our gradient, right? And kind of the step we're going to take. So yeah, you can probably already start seeing the analogy here. Over here, these, like the gradients at all these points along this journey are kind of analogous to these, data points here. And so instead of reacting to like that specific value we just observed, we can do some kind of if we can smooth this out a little bit, it'll be more efficient, which of course will look, in this case, maybe something like this, So just to kind of talk through this guy here a little bit, I don't want to get too deep into this, but why is it called an exponential moving average? So if we kind of break some of this out, expand it, right? This is going to be equal to beta g. So gt minus 1 is the actual observed value at the last time step. 1 minus beta v t minus 2. Okay. So we can just plug that in here. So just an expansion of this recursive series. Okay. Plus, now let's distribute the 1 minus beta term. So you start seeing some patterns emerging here, probably. Okay. And I just go ahead and I'm not going to continue deriving it step by step, but at a certain point, you have something that looks like this, beta, and we're going to just put a 1 minus beta to the 0, which of course equals 1, but just to help us see the pattern, gt minus 1 plus beta minus beta to the 1 power, gt minus 2 plus beta 1 minus beta squared times gt minus 3 plus beta 1 minus beta cubed times g to the t minus 4. Okay, and then ultimately, let me make sure I get this right here. So it's going to be skipping some steps. Okay, and then there'll be another term here, which we're not going to expand. No beta in front. Then here's your next recursive term, okay? But you can clearly see here in this stage a pattern, right? There's here's your data, the actual observed data going back in time, okay? And you can see this coefficient, which your exponent is increasing here each time. This is decaying, so this coefficient beta times 1 minus beta to the some power, that is going to be a decreasing coefficient. So at some point, so basically you can, if you visualize this as kind of like a series, you can write this in like a summation notation, but you get the point here. Basically the value of your moving average at any time step is some exponentially decaying weighted sum of all of your previous values. So you've actually encoded um, your previous observed data into your VT, but notice that there's no memory required here, right? There's just the current observed value and the one previous value of the moving average. That's all you need to compute the current moving average. So it's very computationally efficient. So that's moving averages. And I'm just going to quickly then talk about momentum. Okay. So momentum is an optimizer. So this is like a just naive gradient descent optimizer. It's an optimizer, but it's very simple. And momentum is a step up in complexity. So it's defined as, so you keep a moving average of your gradients. So B, in this case, B t minus 1 plus 1 plus beta gt, where gt is your current gradient. So as we just discussed, keeping track of this moving average of your gradient. Oh, and also I will say that this beta term can be used there's kind of a way to interpret, like, obviously these coefficients decay to 0, so at some point in the past here, like, this old data won't be contributing, effectively at all to the current average. But, you could imagine, like, if you set beta to a certain value, like this would be like a very rapidly changing moving average that only kind of considers effectively the last few data points, or you could configure beta so that it's actually giving weight to like the last 20 or so. And so there's some, and this is kind of a heuristic, I think, but you can, you're like effective kind of size of your sliding window here is something like this. And I will say that so in this case here, they recommend to set beta to 0.9. Okay, and that gives you like an approximate window size of like 15 to 20 or 10 to 20, something like that. Okay, and then so once you have your moving average, and then you compute your model updates as such. Minus your learning rate times the moving average of your gradients. Okay. So the intuition here, let me quickly try to reorganize this. So the intuition here is so basically, so in this case here, there's this oscillating, there's this kind of direction here, the vertical, like up the side of the valley direction, that over each iteration, it's oscillating back and forth in different directions, which will effectively cancel out to some extent in the moving average, so that you are you don't have as much sensitivity to this direction of this like rapid volatility and oscillation. But at each point, the gradient is consistently like pointing a little bit down towards the middle of the valley, the direction we want to go, right? And so like there won't be any like terms canceling out. That consistent direction that we see at every step is kind of like a strong signal that we want to follow. And that's kind of what momentum is getting at from a intuition perspective. Okay. Okay, then let's talk about RMS prop. Okay. It's another variant here. Okay. And it keeps track of, again, using a moving average, but a little bit different. Beta plus 1 minus beta g squared. Okay. So this is an exponential moving average of the squared gradient. Okay, and of course, squaring something is always positive. The result's always positive. So we're kind of, I think in a way, this is kind of keeping track of the overall magnitude of how much gradient we've seen in a certain direction. And then our update to the model weights is going to be okay. So it's basically, so you're kind of normalizing. So this is the actual gradient. There's a learning rate. And in the denominator here, you have a square root. So like basically reversing the squaring that we did just for convenience. An epsilon term to make sure we don't divide by 0. But in effect, this is like kind of damping out in our updates. This is going to damp out, in the denominator here, it's going to damp out directions of the gradient where we've seen like a lot of magnitude. So it's kind of like resisting, again, it's like another, it's pretty heuristic, it's pretty like intuition based, I think. I don't know if there's a lot of theory behind this, but seems to work better. And yeah, it's just this constant trying to come up with tricks, ways to resist, moving too fast in a certain direction. Like we want a stable, like chugging along of the parameters during training. Okay, and then last one we're going to talk about is the atom optimizer. Okay, and the atom optimizer is just a combination of momentum and RMS prop. Okay, so just to write it out, we're going to keep track of a couple different moving averages. Beta 1 times m t minus 1 plus 1 minus beta 1 times g t. Okay, so this is your moving average of the gradient. Okay, we're going to also keep track of beta 2 b t minus 1 plus 1 minus beta 2 g gradient squared. So here's your moving average of the square gradient. So kind of taking, a piece from momentum and a piece from RMS prop here. And again, not going to cover this, but you should just know that these moving averages are biased towards 0 at the beginning of this, because you're only slowly, like you start off at 0, you kind of initialize it to 0, right? And then for the first, let's say 10 data points that you shove into your moving average, like you're only allowing in a certain amount of the data point that you see but due to the beta or the 1 minus beta, less than 1. So it takes a while to kind of warm up. So you'll typically like see a gap here until it catches up. And so Atom, I guess the practical, like what you see in the wild, there's a way to correct for this just by adding another term. I'm not going to get into it, but I will say that we're going to work with the corrected versions of these. And again, not important. You can look it up if you need to. All right. And then our update is going to be learning, right? Corrected version of this plus epsilon, very small number, multiplied by the momentum term, corrected. Okay. So, you can see how this is a combination of the update equations for momentum and RMS prop. There are some recommended values from the authors, 0.9, and then beta 2, 0.999. And, I'm not going to get into this too much, but TLDR is Atom is pretty popular in practice, found to work well. I think these optimizers are, it seems to be kind of like a lot of intuition and effectively hacks, useful hacks. I think there's a big difference between using, your vanilla SGD versus Atom. I think you end up training a lot faster, spend a lot less on compute, and end up with ultimately like more performant models. So there's a big difference. Like, not trying to knock this at all. It's just that there's not like a ton of super theoretically motivated. I feel it seems like it's pretty intuition based, and I guess that's fine. I think an important concept to keep in mind here is that gradient descent is by design I guess what you would call like a first order only optimization algorithm, meaning that it only considers the kind of first derivative of the loss function with respect to the parameters, which is the slope. You can think of that as the slope. There is a second derivative, which I believe is called the Hessian in linear algebra, that talks about the curvature. Again, always though, both the first and second derivatives that we talk about here are defined only at that specific point. Like it's a local information. You don't have information. You don't know what the rest of this loss landscape is. You're just able to via calculus, by taking the first, and technically you could take the second derivative, you can find out information about the landscape around you to inform your movements, your updates to the parameters. The second derivative, curvature, is useful information, and theoretically, I think would you could make smarter updates if you had the second derivative. However, I think in practice it's not really tractable or practical to compute that. I think it's pretty expensive. Um, so we don't. We just kind of, by laws of physics and current computing, we are limited to working with just first derivatives. Um, and yeah, that works pretty well, but it's a little bit ugly. And so I guess, like, if you're like a pure mathematician, taking that perspective on these optimizers, you kind of have to understand that, you know, this is a kind of like a messy, noisy territory that we're working in here. So, heuristics, empirical stuff is necessary and it's effective. And, obviously this is an extremely key part of training neural networks. So this stuff is important. All right, that's it.